Hello everyone. Let us discuss pulse amplitude modulation and demodulation. Important question to answer is that how to transmit digital signal through analog channel. So we have digital data, that means input bit stream is there. So we have to transmit that input bit stream into the channel, which is analog. So when one will be coming, we will be transmitting PT pulse, which may be a plus 5 volt pulse. The shape of the pulse does not matter at present. It can be a positive. It can be a positive polarity sinusoid, and when zero is to be transmitted, we will transmit minus 5 volt, or it can be negative sinusoid, negative polarity sinusoid. So the pulse shape does not matter at present, but I am taking a pulse to represent 1 and minus PT pulse to represent 0. For example, this is the bit stream 10110. So and the symbol period or the time period of this plus 5 volt corresponding to this one will be known as the symbol period, right? It will be from 0 to capital T seconds. Okay, so when 1 will come, it will be first symbol. When 0 will come, it will be the second symbol. For example, this is the bit stream. So this 1 comes, this is the first symbol, second symbol, third symbol, fourth symbol, and fifth symbol. So for corresponding to the first symbol, it will be plus 5 volt for 0 to capital T seconds. Next 0 comes, so it will be minus PT pulse. So if it is a minus 5 volt, so that means the corresponding to this 0, it will be minus 5 volt from T seconds to capital 2 T seconds, right? Then from 2T seconds to 3T seconds, it will be again plus 5 volt, 3T to 4T, it will be again plus 5 volt, and from 4T to 5T, it will be minus 5 volt. That means minus PT, and so on. The bit stream will continuously be coming. So if 1 is to be transmitted, we will transmit PT, and 0 is to be transmitted, we will transmit minus PT. So this is known as baseband modulation, correct? Or we can also say that it is pulse amplitude modulation. I will come to that in the next slide. This will be particularly known as baseband modulation. Since we are not multiplying it with a carrier signal, carrier waveform, a high frequency signal, we are not multiplying at present. We are using a baseband signal, baseband waveform, which is PT for 1 and minus PT for 0. Now let us allocate, let's continue with the same example. So if I'm taking 10110, that does not mean this is only the bits. The bit stream is continuously coming, and we have to actually do the baseband modulation so that these bits are to be represented with waveforms. So if one is, let us call this first bit, for example, as B0, then B1, B2, B3, and so on. So these are the bit values. Now to these bit values, we have to allocate pulse waveforms, or we have to allocate uh, amplitudes, either plus 5 volt or minus 5 volt. And second thing we have to do is we have to select a waveform, the shape of the waveform. At present, I am selecting, to explain, I am selecting a rectangular pulse, which I call as PT, and the amplitude I am selecting of that waveform is plus 5 volt, right? So it is amplitude multiplied with this waveform. The shape of the waveform will give me the resultant waveform corresponding to this one, and so on. So there has to be a mapping from if the digital bit is 1, it has to be represented with a plus 5 volt. At present, I am taking a rectangular waveform, so it will be plus 5 volt rectangular waveform. When 0 is to be represented or sent across the analog channel, so it will be minus 5 volt of what? Of PT. So minus 5 will be multiplied with the pulse waveform to get minus 5 volt resultant waveform to represent 0, and it is to be transmitted to the channel. So this is known as bits to level transformation, and this transformation is known as mapping. This mapping is bits to levels, right? So in general, how can we define this transformation? Now this is the from 0 to capital T seconds. There is a pulse pt. It has to be multiplied with amplitude a0, right, corresponding to this pulse. So it will be a0 pt. From to t to capital T seconds, it will be again multiplied with certain amplitude, right, and then it will be multiplied with the pulse waveform. So corresponding to 0, it will be a1 pt minus capital T, because it is a delayed, this waveform from capital T seconds to 2t seconds is delayed by capital T. So that is why a1 pt minus capital T, and this third bit will be 1 again. So it will be a2 pt minus uh, 2 capital T. 1 will be a3 pt minus 3t, and this 0 will be a4 pt minus 4t. So these a0, a1, a2, a3, a4, these are the amplitudes, right? In our case, at present, it is either plus 5 volt or minus 5 volt. Then the pulse will be multiplied, the pulse shape, pulse waveform, the pulse shape will be multiplied with these voltages, right? So because 1 is being represented with plus 5 volt, 0 is being represented with minus 5 volt. So this is known as pulse amplitude modulation. Why? Because we are using pulse amplitudes to represent ones and zeros. And this is also known as baseband modulation. At present, we are not multiplying it with any carrier signal, any high frequency signal. This is a baseband low pass complex waveform. All right. Then, in general, if this is how these bits are to be represented individually, a0 pt, a1 pt minus capital T, a2 pt minus 2 capital T, and so on. So how can we in general put this waveform into an expression? So in general, we can say that the transmitted signal is represented as xt, which is the transmitted signal. K going from minus infinity to infinity, K is an index, AK, right? So K will vary from 0 minus infinity to infinity. It can be A0. So when K is 0, it will be A0 PT and so on. When K is 1, it will be A1 PT minus capital T. When K is minus 1, that is the previous to the present waveform, if we are talking, then it will be A of minus 1 pt plus capital T. So this waveform actually represents the baseband modulation, right? Ones and zeros are represented by pulse amplitudes, correct? And since no high frequency signal is being used as a carrier, and this is known as baseband modulation. So we are representing PT as a rectangular pulse, but it can be of any shape, as I have already explained. It can be this shape also, which we call as PT. It can be this shape also, which we call as minus PT. Right. So these have to be then multiplied with the amplitudes to do the mapping. Now it can be like this also. It can be it can be overlapping pulses also, right? So we will particularly talk about these overlapping pulses once we will come across with the intersymbol interference and those concepts. But I will describe those concepts in detail once we will reach to that point. But at present, we have to understand what is baseband modulation. Now, if we are using rectangular pulse, and if we take the Fourier transform of a rectangular pulses, we know that it's a sinc function. So it is a complex. So the spectrum clearly tells us that it is complex low pass spectrum. If we are using a rectangular pulse to represent either 1 and 0, 1 will be represented with plus 5 volt multiplied by PT, and 0 will be represented by minus 5 volt multiplied by PT, correct? And if we take the Fourier transform of a rectangular pulse, it is a sinc function. clearly it tells us that the spectrum of the rectangular pulse is complex, right? It is low pass since the spectrum is centered around zero frequency. Now each pulse, because we are transmitting multiple rectangular pulses representing ones and zero as a bit stream. So each pulse is a sync pulse in frequency domain. A bit stream will also lead to a waveform similar to sync. So if we talk about a digital bit stream, multiple collection of bits, so every individual bit will have a Fourier transform of sync function. Now, if we collectively try to take the Fourier transform of the collective waveform, then it will again be representing some kind of sync pulse in frequency domain. So we need not to use rectangular pulse. The question is that we need not to use rectangular pulse always. What is the optimum waveform to use to design a communication system that we will reach to that point after going through all the fundamental concepts. So the question is, what is the optimum design of the pulse? So we will reach to that level and we will travel a distance where we will explain the fundamental concepts of communication systems. Now, next, because we are taking a rectangular pulse here to represent ones and zeros, for example, as an example, I'm taking the rectangular pulse. So if I'm taking a rectangular pulse, we know that the Fourier transform of this rectangular pulse is a sinc function, right? And I have also explained that the Fourier transform of this rectangular pulse is a sinc function, which is a complex low pass spectrum. Now the question is, up till here I discussed about the baseband modulation. No carrier frequency was there, and the spectrum is centered around zero frequency. Now, in case of passband modulation, what we will do is we will multiply this PT pulse with a carrier signal, high frequency signal, sine 2 pi f naught t. So we will multiply the rectangular waveform with a carrier signal which is sine 2 pi f naught t, and this will be the shape of the pulse. So this is my rectangular pulse, and I am multiplying it with the carrier high frequency signal sine 2 pi f naught t. And if I take the Fourier transform of this resultant signal, what I will get is I will get a sync waveform centered around f naught and a sync waveform on the negative side which is centered around minus f naught. So when I am multiplying this pt with sine 2 pi f naught t, which is a carrier signal, high frequency carrier signal, so when I take the Fourier transform, what I will get? I will get the sync function again, but one part of the sync function will be centered around f naught, the other part will be centered around minus f naught. Now this is a band pass signal, because the center frequency is centered around f naught. It's not extending to zero, right? This type of modulation, if we will try to represent ones and zeros, and we will try to send those ones and zeros, which is digital data, into the analog channel, and using a carrier frequency we are multiplying the PT pulse, then this will be known as the passband modulation. And what is this pulse? PT sine of 2 pi f naught t. So PT is sine 2 pi f naught t. I will call this waveform, which is a representation of this waveform. This is a rectangular periphery, and inside the rectangular periphery is the sinusoidal waveform, which is PT sine 2 pi f naught t. I call this pulse as P dash t. Now if I use the Euler's formula, I can put e to the power j2 pi f naught t minus e to the power minus j2 pi f naught t by 2j, representing this sine 2 pi f naught t. Right? I can substitute values like this. Now this is known as passband modulation. P dash T. What is P dash T? P dash T is the passband pulse. PT is the baseband pulse. Baseband pulse, meaning by it is not multiplied with the carrier signal. P dash T is again the periphery is a rectangular waveform, but it is multiplied by high frequency signal. P dash T is the passband pulse to be transmitted. Again, it is representing ones and zeros because it is to be transmitted to cover a longer distance. So it is a passband pulse. Whereas PT will be used as a baseband modulation pulse, and um, it is not used to transmit to cover longer distances. So it is a baseband pulse, and P dash T is a passband pulse. But P dash T or PT, they represent the pulses to be transmitted, and these pulses will represent the digital data ones and zeros. Okay. Now, in case of passband modulation, I can use the same expression here, which is xt is my transmitted signal, ak pt minus k capital T. This was for baseband modulation. Now I have changed this waveform into a passband pulse. So again, the signal is to be transmitted. The signal to be transmitted is now p dash t minus capital kt. Now the question is that where this baseband modulation is used. For example, in your inside a computer, if you are trying to communicate between the different devices, then you have to transfer the information in terms of some pulse waveform, because you have to transmit it through tracks or wires. Right. So baseband modulation, the good example to explain baseband modulation is the communication inside a chip or inside a computer. Right. You use waveforms to transform the data. You're not covering a large distance. Right. So that you have to multiply it with the carrier. You need not to multiply it with the carrier, but when you have to cover longer distances, you have to multiply it with the carrier. We have already discussed the need for modulation. Right, need for modulation, meaning by that how you modulate the message with the carrier signal. All right, but ultimately, so here it is p t minus k capital T, and here it will be p dash t minus capital K. So this is the passband modulated pulse. Now this type of modulation, whether baseband or passband, is called pulse amplitude modulation, because we are using the amplitude, either plus 5 volt or minus 5 volt as an example, to represent ones and zeros. And this is also known as amplitude shift key, pulse amplitude modulation. So we have two types of modulated pulses. One is the baseband modulated pulse, the other is the passband modulated pulse. Okay. More bits can be combined to be transmitted in one symbol period. Now, the question is that in the previous, up till this point, I was using the symbol period from 0 to capital T seconds to represent only one bit, either 1 or 0. But I can combine within that period from 0 to capital T, I can combine two bits. That means I can send either 00, 01, 10 or 11. Four combinations can be there. If I combine in that symbol period two bits, right? So it can be 00, 01, 10 and 11. So that's what I'm trying to explain here. So more bits can be combined to be transmitted in one symbol period. Earlier I was using either 1 with 5 plus 5 volt, 0 with minus 5 volt. So this is known as 2 PAM. Because how many levels are there? Two levels are there, either plus 5 volt or minus 5 volt. So it is 2 PAM, or two levels are there. This is of course known as mapping. Now I am saying that within the symbol period, I am trying to combine two bits rather than one bit. Either I can send 00, either I can send 01, 10, Now I will have to represent this 0 0 with certain amplitude. So let's say I am representing it with 1 volt. So what will be my what will be my baseband pulse? 1 into pt. For 0 1, I choose my level as 2 volt. So the waveform will be 2 times pt. 103 volt, 3 times pt. 114 volts, so 4 times pt. So 100 transforming 00 to amplitudes. This is mapping, and this is my baseband. This will be my baseband modulation pulse. For 00 it will be 1 volt, for 01 2 volts, for 11 it will be 4 volts, and 01 it will be 2 volts. If let's say this is the data I want to transmit, 00 01 11 and 01. So this is my transmitted signal. Since 4 levels are there, now it will be known as 4 PAM. I can club 3 bits also, 000 So how many levels in that case will be there? 8 levels. So that will be known as 8 PAM. And in general, I can combine, if I can combine capital M bits, so how many levels will be there? 2 raised to the power M levels will be there. And this type of modulation in general is known as M-array PAM. MPAM. So if M levels are there, how many bits are there? I'm trying to combine. B bits I'm trying to combine. How many levels will be there? M. So 2 to the power B will be equal to M. So what is that PAM known as? That is known as MPAM or M-array, A-R-Y, M-array PAM. If I use only one bit, it will be binary PAM, right? If I use B bits, it will be M-array PAM. Why binary PM? Because I am using one bit within the symbol period. So how many levels will be there? 2 levels will be there. So it will be binary PAM. But if I'm using B bits, it will be 2 raised to the power B will be equal to capital M. So it will be known as M-array PAM. So B bits, M levels equal to 2 to the power B. Right. So this is modulation. This is pulse amplitude modulation. Now, of course, we have to transmit the signal through the channel. So once the signal goes through the channel, it will be distorted. It will be met with noise. It will be meeting with the noise. Noise will be added into the signal. So it will be a distorted and noisy signal. So if we transmitted one for corresponding to this 1011, if we transmitted this signal, what we will receive is this kind of noisy signal. Let's assume it is AW, additive white Gaussian noise. So we receive this kind of signal. Now at the receiver end, once we receive this noisy signal, how to demodulate, how we will come to know that within this period what was transmitted from 0 to capital T, what was transmitted. Since it is a noisy signal, so one way to demodulate is to sample at a particular point. We will try to find out the voltage at a particular point, and if it is a positive voltage, we will say that it is plus 5 volt, and we will make a decision that 1 was transmitted. And if the voltage is negative, then we will say that detected voltage is negative, then we will say that it was minus 5 volt and 0 was transmitted. So one way to demodulate is to sample at a particular instant in the symbol period. Now if the value is positive, we will say it is 1. If the value is negative, it is 0. But the question is that at the sampling instant where we are trying to take the voltage from the received signal, noise has corrupted the signal so much that the voltage which was supposed to be positive voltage, at that point only it becomes negative. So it will make a wrong decision at that point. It was to make a decision in favor of 1, but wrongly it will make a decision that 0 was transmitted. Right. So what we can do is that instead of measuring the voltage at a particular point, we will try to take the average of average from 0 to capital T using this integral. from 0 to capital T yt dt. That means we are trying to find out the area under the curve from 0 to capital T. This is the received signal. So we can take all these samples and integrate all the values within the symbol period. So if this value is greater than 0, it will be 1. If this value is less than 0, it will be 0. This is in case of 2 PAM, when only two levels are there, when only one bit is there in between the in the symbol period. Had it been more bits combined within the symbol period, then of course we will note down the amplitude value. It will not be, the decision rule will not be greater than or less than 0. It will be, if it is within 0 to 1 volt, let's say, it will be 0 0. If it is from 1 volt to 2 volts, it will be 0 1 and so on. Correct. So this is how actually the demodulation will be done. This is demodulation. So this is this taking the integral, taking the average, taking the area under the curve, knowing the voltages is actually known as demodulation of PAM signal. Now in general, what we will do is we will have a received signal yt, right? We will try to find out ak, what is the amplitude, after integrating it over 0 to capital T. We will try to find out the amplitude, and then we will be assigning from that amplitude which we have detected, we will be assigning whether what combination of bits was transmitted. This is transforming from detected amplitude levels to bits is known as demapping. Earlier it was going from BK to AK, that means mapping bits to levels is known as mapping. Doing the transformation from the excuse me, doing the transformation from amplitude levels to bits is known as demapping. And we will try to, and in this detection from, because yt is the received signal, we are trying to detect the amplitude. So that means we will be getting ak hat, the estimate of the amplitude. And in general, if we try to put this demodulation in a general expression, we will take from kt to k plus 1t. It is again from within the symbol period only, but in general, I am trying to explain here. So, integrating from kt to k plus 1t yt dt is actually equal to ak hat, which is estimate of ak, because ak was transmitted from the transmitter side. At the receiver end, we are trying to estimate what is the amplitude. So we will call it ak hat. Now yt is the signal that is received. So we can say in general that yt will be equal to pt minus kt. Yt is the signal, and of course it is to be multiplied with p times t minus kt, right? So this is the received signal yt. If we try to express from minus, this is only one corresponding to one symbol period. But if we are trying to estimate from all the symbol periods in terms of a complete waveform, so it will be minus infinity to plus infinity yt pt minus capital kt. And we can just do the little manipulation here. I will add one capital T and I will subtract one capital T. So I can express this waveform like this: pt minus k plus 1 capital T plus t. Right. So this, if you look it carefully, this is actually the convolution formula. Convolution of what? Convolution of this waveform p capital T minus small t with yt, which is the received signal. Let me explain you once again what we are trying to do. Yt is the received signal. We are trying to estimate ak. So what amplitude was transmitted, and we will be transforming. We will do the demapping from the level detected or estimated. We will demap into bits. So in general, ak hat, which is the estimate of the amplitude, can be expressed as one symbol period integral of yt dt, which I express as kt k plus 1t. and I can extend this relationship further, going from minus infinity to infinity. It will be yt pt t minus kt, right? A complete waveform, all the bits which all the waveforms which we are receiving, I can express that waveform like this, and I try to manipulate it t minus adding t and with subtracting t. I can say that this is the convolution formula, and the convolution is happening between p t minus capital T minus small t and yt, which is the received signal. And this convolution is to be sampled at capital T seconds. So small t will have to be k plus 1 capital T. Then only because I have to when I will sample at a particular capital T, then only I will get the estimate of AK. All right. Then this integral has to be sampled at t small t equal to k plus 1 capital T. That means that at the completion of every symbol period, we have to perform the convolution of the received signal with this pulse, which is basically this, and we will be getting the estimate of the AK. So equation 3 turns out to be equal to 4. So that means this equation, if I what I have done is I have tried to explain within one symbol period this, I wrote this expression. Then in general, I try to extend the waveform like this. And if this waveform is sampled at capital T seconds, then this fourth equation and third equation, they are same. They are representing the same result, which is the convolution or filtering. This is basically convolution, or we can also say that this is kind of filtering. So what this explains actually? This explains me yt is the received signal. If I pass this received signal through a filter, what should be the response of that filter? Pt minus capital P of t, which is capital T minus t, right? P capital T minus t. If we pass the received signal through a filter, that's what I'm trying to explain here. If we pass a signal yt through a filter with impulse response P capital T minus T and sample the output of this filter every capital T seconds, I will be getting the estimates of the amplitudes A0, A1 and so on, and then I can demap to bits, estimates of AK, and then I can do the demapping and I can extract the bits, what bits were transmitted. So yt is filtered through a filter with impulse response ht equal to p of capital T minus small t, and then sample at t instants of time and then do demapping to extract the bit stream. This concludes the demodulation of the received signal, right? Demodulation of pulse amplitude modulated waveforms. And this filtering is, we will see that this is actually this impulse response actually represents the matched filtering. I will explain to that point later, because this waveform, this filter response, the response of this filter is what? Pt minus t. What was Pt? Pt was the pulse to be transmitted. Now the filter response is matched to the shape of the pulse, right? The filter that we are trying to use at the receiver end is actually matched to the pulse shape which we are transmitting, which we are using to transmit the digital data. So that is why this filter will be known as the match filter. So we will discuss more about match filtering and other things in detail. So I finish my lecture here, which is of course for the pulse amplitude modulation and demodulation. Thank you very much. Thank you.